Lesson 1, Electrical System. As this engine runs, it is controlled by the electrical system. The starting sequence, operation, and shutdown sequence are all controlled by the electrical system. When you have finished this lesson, demonstrate your understanding of the material by taking the first the voltage of the generator. Now, the two electrical systems, however, are not completely separate. As you will see in later lessons, the two interface in several places to control both the generator and the engine. The DC control system includes all of the components that receive or carry direct current to of events during the startup cycle is controlled by the DC system. A variety of switches, timers, monitors, and other devices are used to sequence and activate the components of the fuel, start, and generator systems. Now, you may already be familiar with, for instance, the start switch S101, the prelude timer KT222 located inside the console, and, as an example, another item of hardware that's controlled here, the electro-hydraulic actuator on the package. Now, they are part of the controls for the start sequence. Now, as each of these components receives a DC signal, an event is started or stopped. Now, when the engine is operating at 100% speed, the DC control system makes adjustments as load is added or taken away and monitors engine performance. DC control system also activates the shutdown sequence. Let's take a look at some of the components of the DC electrical system. There are two types of timer relays used in the electrical system. The time delay pickup relay waits for a preset time period before transferring contacts. When the relay is energized, a timer begins. When the time period is up, the contacts of the switch will transfer. The gas purge time delay is an example of the time delay pickup relay. When it is energized, a 10-second timer begins. At the end of the 10 seconds, the relay contacts close and energize the primary fuel valve. The second type of relay is the time delay dropout relay. Contacts on this relay transfer when the relay is energized and retransfer at the end of the timed period. An example of the time delay dropout relay is KT220, the post-lube timer. KT220 is energized when the engine starts and transfers its contacts. When the engine shuts down, the timer is de-energized and begins time a 55-minute time period. At the end of this time period, the relay retransfers its contacts, causing the post-lube pump to shut down. Remember, the time delay pickup relay begins timing immediately, then transfers its contacts. The time delay dropout relay transfers its contacts when energized and begins timing when it is de-energized. At the end of the timing cycle, the contacts retransfer. Now, these two types of relays are used to control the sequence of events during startup and shutdown. Now, another component in the DC control system is the transducer. A transducer converts one form of energy into another. For example, the magnetic pickup, as seen here, converts rotational motion into electrical energy by electromagnetic induction. Two other types of transducers are used to sense heat in the turbine and generator. As an example, the thermocouple seen here is used to measure engine temperature. Resistance temperature detectors, otherwise known as RTDs, are used to sense heat buildup in the generator. The resistance of the RTD changes with changes in temperature. For example, when the heat increases, the resistance of the RTD will change, causing a change in the amount of current flowing through the RTD. The change in current is then monitored for an indication of temperature level. Another type of transducer is the thermocouple. The thermocouple converts engine heat into electricity that is sent to the engine temperature monitor. The third type of transducer is the magnetic pickup, situated here on the gearbox. Magnetic pickups monitor the rotation of the gears in the reduction drive gearbox. The motion of the gear is converted by the magnetic pickups into electrical energy, which is sent to a control unit for processing. Now, the transducers in the DC system convert heat or mechanical energy into electrical energy. The electrical signal then sent elsewhere in the DC system for monitoring. The AC control system monitors and controls generator output. The AC system makes adjustments in the exciter field during operation to increase or decrease generator output with change in load. The voltage regulator has two operating modes for controlling generator output. When the voltage regulator is placed in the isochronous mode, the generator's output is kept constant with changes in load. Generator output, however, will change with load demands when the voltage regulator is in the droop mode. The AC system incorporates four types of transformers to supply voltage for operation. The current transformer is very accurate and consistent in its output. The current transformer steps up or steps down amperage for use by the instrumentation. The watt var, the ammeter, and the frequency meter use the current transformer's accurate output to measure generator performance. The potential transformer is also very accurate but steps up or steps down generator output voltage as opposed to amperage. Voltage from the potential transformer is sent to the voltmeter, the watt var meter, the frequency meter, and synchroscope. The third type transformer shifts the phase angle of the voltage. The phase shift transformer sends its output to the watt var meter as a measure of reactive power. The fourth type of transformer in the AC system is the power transformer. The power transformer is used to supply voltage and current when a high accuracy is not needed. Remember, the turbine package's electrical system includes both a DC system and an AC system. The DC system primarily controls the turbine engine, while the AC system primarily controls the generator. There are some instances when the AC and DC systems work together to control both the engine and generator. Controlling functions of the two systems will be discussed in the other lessons of this module.
You have just viewed the lesson on the electrical system. Let's review the important points. The DC system controls the sequence of events that occur during the startup and shutdown cycle. Two types of relays are used in the system to time the sequence of events. When the time delay pickup relay is energized, a timer begins a preset time period. After the time period is over, the contacts transfer. The contacts of the time delay dropout relay transfer when the relay is energized. When the relay is de-energized, the timer begins to time out a preset time period. At the end of the time period, the contacts of the relay retransfer. The transducer converts one form of energy into another form of energy. The magnetic pickup converts mechanical energy into electrical energy. The resistance temperature detectors change the electrical signal with changes in temperature, and thermocouples change heat energy into electrical energy. The AC electrical system incorporates four types of transformers. The potential transformer and current transformers provide the AC system with a consistent electrical output. The phase shift transformer changes the phase of the generator output for use by the kVAR meter. And the power transformer provides the AC system with voltage and current. You have just completed this lesson. Now turn to your learning guide for review. If you wish to test your understanding, stop the tape and take the progress check. Lesson 2, Engine and Generator Control System. This engine is controlled by a number of small, solid-state electronic devices. Each of these black boxes receives a signal from a monitoring device indicating the engine's performance. Through electronic logic, the black boxes monitor speed and temperature during operation for engine sequencing and protection. When you have finished this lesson, demonstrate your understanding of the material by taking the progress check on the following performance objectives. First, identify the devices that control the servo actuator. Second, describe the functions of the engine speed monitor. Third, describe the functions of the engine temperature monitor. Fourth, describe functions of the speed and load control unit. Fifth, describe the function of the voltage regulator. Here is your instructor.
The engine is controlled by several solid-state electronic devices located here in the control console. Located across the back of the console, as an example, are the engine temperature monitor, labeled Z282, the speed monitor, Z283, the main fuel actuator control, Z244, and the ramp generator in the upper left-hand corner, Z249. Down here is the speed and load sensing control, Z251. Now let's take a closer look at the functions of each of these black boxes. The speed monitor in the center, for example, is part of a subsystem we will refer to as the speed control subsystem. The input signal for this subsystem is provided by the magnetic pickup G383, located here on the reduction drive gearbox. The magnetic pickup converts the rotational motion of the gears into an electrical signal which is sent to the engine speed monitor, Z283. When the engine is running, the speed monitor receives a constant signal from the magnetic pickup. The speed monitor converts the signal into engine speed, which is displayed on the engine speed meter. The speed monitor has 4 gates which transfer at preset speeds. When a gate transfers, one or more relays are energized, causing other functions to take place in the engine. For example, the closed contacts of gate number 2 send signals to more relays. Some cause the starter system to deactivate, and others flash the field of the generator. The engine temperature monitor, Z282, located here next to the speed monitor, is part of the engine temperature control subsystem. The engine temperature control subsystem activates various components to increase, decrease, or maintain engine temperature. The input signal for this subsystem comes from the thermocouples located here on the aft end of the package. The 6 thermocouples send a signal to the temperature monitor. The temperature monitor, Z282, converts the signal from the thermocouples into engine temperature, where it is displayed on the engine temperature meter. The thermocouple signal also transfers the 3 gates in Z282. The first gate selects the component to control the servo actuator. The other 2 gates on the temperature monitor are for the impending high engine temperature warning and for the high engine temperature shutdown malfunction. First, gate number 2 will activate the warning system, as indicated by warning light number 26. Now, if the condition is not corrected within 5 seconds, the engine will shut down. If at any time the temperature were to increase to the set point of the 3rd gate, the engine would shut down immediately. Now, another subsystem located inside the control console is the speed and load control subsystem, or governor Z251. Z251 is located here, lower in the console area. The governor panel includes an amplifier, ramp generator, load sensor, and speed sensor. Now, this subsystem has 2 input sources, one for engine speed and one for load. Magnetic pickup G351 sends a signal to the speed module. 3 current transformers send a signal to the load module, indicating the output of the generator. When the engine reaches 90% speed, the governor takes over the control of the servo actuator. Corrective signals are sent to the servo actuator from the governor anytime engine speed goes above or below 100% speed. Now, during parallel generator operation, the governor maintains equal load sharing between the generators. Signals from the 3 current transformers are sent to the load modules of the governors, indicating generator load. If the load module senses that one of the generators is carrying too much load, the governors will send a signal to the servo actuators to change the amount of fuel being sent to the engines. Let's take a closer look at how the servo actuator is controlled. Now, first we know the signals are sent from the ramp generator and main fuel actuator control, as well as the governor, to the servo actuator. And second, we know that the temperature monitor, speed monitor, and governor control determine which device will control the servo actuator. As the engine begins to rotate, the magnetic pickup G383 sends a signal to the speed monitor. Gate number 1 of the monitor will transfer contacts at 15% speed, energizing KT241. At the end of the 10-second time period, contacts are transferred, which turn on the power to the ramp generator Z249. An output voltage ramp is sent to the servo actuator to increase the fuel flow to the engine for ignition. With ignition, the temperature of the engine increases, as does the signal from the thermocouples to the temperature control. When the temperature control unit senses 350 degrees Fahrenheit or 177 degrees Celsius, K239 is energized and transfers the control of the servo actuator from the ramp generator to the main fuel actuator, Z244. The main fuel actuator then increases the signal to the servo actuator, calling for increased fuel flow. If the temperature monitor senses too high a temperature, a signal will be sent to the main fuel actuator control, which in turn sends a signal to the servo actuator to decrease the fuel supply. The engine continues to increase its speed as the fuel is increased in proportion to the maximum acceleration schedule. When the engine speed reaches 90%, gate number 3 on the speed monitor closes. Relay K263-1 is energized and transfers contacts. The transfer of K263-1's contacts transfers the control of the servo actuator from the main fuel actuator to the governor. The signal from magnetic pickup G351 to the governor speed sensor indicates 90% speed. The governor then sends a signal to the servo actuator to hold the fuel flow to the engine at maximum acceleration schedule. When the engine is near 100% speed, the governor sends a signal to the actuator to reduce the fuel flow and maintain a speed of 100%.
So far, we have identified the three subsystems that control the servo actuator. The next electrical control subsystem controls the output of the generator. The voltage regulator, VR260, controls the output of the generator. The voltage regulator subsystem receives an input from current and potential transformers which monitor generator output. The voltage regulator then compares the generator's output with a preset output level. Changes in the flow of DC current through the brushless exciter in the generator are made by VR260 to maintain a constant generator voltage output with changing loads.
You have just viewed the lesson on the engine and generator control systems. Let's review the important points. The electro-hydraulic actuator is controlled by the ramp generator, main fuel actuator control, and governor. A magnetic pickup sends signal to the engine speed monitor, which activates a series of relay at 15%, 66%, 90%, and 108% engine speed. The engine temperature monitor receives an input from each of the thermocouples and sends signals to select ramp generator or main fuel actuator. The governor receives input from a magnetic pickup and from current and potential transformers. At 90% speed, the governor takes over the control of the servo actuator. At 100% speed, the governor acts to maintain a constant frequency and equal load sharing between parallel generators. Generator output is controlled by the voltage regulator. The voltage regulator changes the flow of DC current through the brushless exciter control generator output. You have just completed this lesson. Now turn to your learning guide for review. If you wish to test your understanding, stop the tape and take the progress check. Lesson 3, Protective Monitoring Systems. Excessive speed, temperature, and vibration are malfunctions that could cause damage to your package. The turbine package is built with a standard protective monitoring system and may include some optional protective equipment to prevent damage to the engine or any of the package components during a malfunction. The protective monitoring equipment will initiate a malfunction shutdown automatically when a damaging condition exists. When you finish this lesson, demonstrate your understanding of material by taking the progress check on the following objectives. First, describe the purpose of the engine overspeed and backup overspeed monitors. Second, describe the function of the gas and flame detectors. Third, describe the function of the vibration monitor. Fourth, describe the high engine temperature malfunction shutdown sequence. Fifth, identify set points of the over and under voltage relays. Here is your instructor.
Most of the protective monitoring systems are a part of the DC control system. Each of the monitoring systems can shut the engine down when malfunction occurs to prevent damage to the package or the surrounding environment. Now, before I describe each of the monitoring devices, let's take a closer look at how the engine is shut down on a malfunction. All of the monitoring devices are connected to one of these malfunction controls located here on the back of the console door. Each malfunction control, Z189, is in fact a printed circuit board with 5 separate circuits. The malfunction board has 5 switches leading to 5 separate malfunction lights. During normal engine operation, the protective monitoring device completes a circuit to a malfunction lockout relay to keep it energized. If a malfunction condition develops, the monitoring device will transfer contacts, causing a malfunction lockout relay to de-energize. 2 events will happen now. First, on the malfunction board, an electrical circuit to the malfunction shutdown light will be closed and the light will illuminate. Second, the de-energizing of the malfunction relay will interrupt the electrical circuit to the start-run relays K210, causing them to de-energize the engine to shut down. The engine cannot be started until the reset button is pushed. Now, Solar has designed this step into the system so that you will have to visually check the engine systems before restarting it, thus preventing the possibility of another malfunction shutdown or damage. Now, some of the monitoring devices may have a warning set point that causes a warning light and horn to go off before the engine actually shuts down. The warning light and horn are not part of the malfunction board. Rather, they are controlled by the protective monitoring units. For example, the speed monitor will shut the engine down immediately upon reaching 108% speed. The vibration monitor, however, initiates a warning light and horn when vibration reaches 0.75 mils. If condition corrects itself, the light will extinguish. But if the vibration increases to 1 mil, the engine will be shut down. Now let's take a closer look at each of the protective monitoring systems. The engine is protected from overspeed by 2 separate systems. The first system, part of the engine speed control monitor, will shut the engine down at 108% speed. If, however, the first system fails, the backup overspeed monitor will shut the engine down at 110% speed. You may recall from lesson number 2 that the engine speed monitor G283 receives an input from magnetic pickup G383 located here on the reduction drive gearbox. When the speed monitor receives a signal indicating 108% speed, gate number 4 will transfer. The change in closed contacts will remove the voltage from the malfunction lockout relay K277. The circuit to the malfunction light will then close, illuminating the light, and the circuit to the ready-to-run relays will be interrupted, causing the engine to shut down. If the engine speed monitor does not shut the engine down at 108% speed, the backup overspeed monitor Z253 will shut the engine down. Z253 is located in the engine gauge panel mounted on the skid. The monitor receives signal from a magnetic pickup mounted on the compressor case and monitors the speed of the first stage compressor rotor. When the backup overspeed monitor senses 110% speed, Z353 will open gate number 2, causing the contacts in backup overspeed relay K353 to transfer. The new circuits created by K353 will cause the start-run relays to drop out and malfunction light number 11 to illuminate. Remember, the engine cannot be restarted until you push the reset button, if it has shut down on an overspeed malfunction. The package is protected from explosive gases and fire by 2 other monitors. The gas monitor Z299 receives an input signal from sensing device G399 located in the package enclosure. If the amount of gas inside the enclosure reaches 20% of the low explosive limit, Z299 will activate warning light number 48 and the horn. If the gas continues to increase to 60% of lower explosive limit, the monitor will transfer contacts, causing malfunction light number 24 to illuminate and the start to run relays to drop out. The flame detector Z398 and Z398-1 monitor the package for fires and will activate a fire extinguisher system if a fire is detected. Z398 and Z398-1 receive a signal from the flame sensors G399 that are located inside the package enclosure. The detectors are sensitive to ultraviolet light and will send a signal to the monitor when a fire is sensed. The monitor will transfer contacts in a relay, causing the malfunction light to illuminate and the engine to shut down. If a fire extinguishing system is included in the package, it will also be activated. The vibration monitor, Z184, will be located on the console door. The vibration monitor receives an input signal from two transducers located on the engine, Z384-1, and the gearbox, Z384-2. The signal from the transducers is displayed on the recorder and meters of the monitor. If the monitor senses 0.75 mils of vibration, it will initiate a warning signal. If the vibration increases to 1 mil, the monitor will indicate a malfunction shutdown, causing malfunction light number 19 to illuminate and the K210 starting relays to drop out. The generator winding temperature monitor, Z170, and the generator bearing temperature monitor, Z170-1, are both optional. If your package includes these two monitors, they will be mounted here on the console door. This package includes Z170. Both monitors receive an input from RTDs located in the generator windings or bearings. The first set point of each monitor is a warning that the temperature is approaching the shutdown point. If the temperature continues to rise to the second set point, the monitor will initiate a malfunction shutdown. The next three monitors are located in the console. Now, you are already familiar with the engine temperature monitor, Z282, located near the top of the console. If the monitor senses an engine temperature of 1155 degrees Fahrenheit or 624 degrees centigrade, gate number 3 will transfer and initiate a warning alarm. If the temperature does not decrease in 5 seconds, a malfunction shutdown will occur. If the engine's temperature should increase to 1220 degrees Fahrenheit or 600 degrees centigrade, the engine would shut down immediately on a high engine temperature shutdown and illuminate malfunction light number 4 on the console door. Now remember, the engine cannot be restarted again until you push the malfunction reset switch. The last two protective devices monitor the generator's output. The under voltage relay Z266 and the over voltage relay Z268 are located inside the console. Beneath the governor, the under voltage relay will shut the engine down if the generator's output falls below 85%. The set point, however, can be adjusted between 85 and 120 volts AC. The over voltage relay will shut the engine down if the generator's output increases to more than 120% normal generator output. Remember, these are some of the malfunction shutdown components included on your package to protect you and the engine from potential damage. If your engine does shut down on a malfunction, you should try to determine the cause before restarting the engine.
You have just completed the lesson on some of protective and monitoring devices. Let's review the important points. Each of the monitoring devices is connected to a malfunction board that will illuminate a malfunction light indicating the cause of the shutdown. If a malfunction should occur, the K210 start-run relays will drop out, causing the engine to shut down. The speed system includes an overspeed shutdown in the engine speed monitor and a second system in the backup overspeed monitor. The gas and flame monitors will protect the engine from explosive gases and fire. The engine vibration monitor has a warning and shutdown point to protect the package from damaging vibrations. The generator winding temperature monitor and bearing temperature use RTDs in the generator to protect it from overheating. The engine has two shutdown set points for high temperature. If the engine's temperature reaches the first set point, there is a 5-second delay before shutdown. If the temperature should reach the second set point, shutdown is immediate. The undervoltage and overvoltage relays monitor generator output and will shut the engine down if the generator's output decreases or increases above their set points. You have completed this lesson. Now turn to your learning guide for review. If you wish to test your understanding, stop the tape and take the progress check. Lesson 4, Governor System. The governor system is used to control the speed of the engine during varying generator load conditions. The governor senses engine speed and kilowatt load and sends signals to the servo actuator to make appropriate changes in the fuel flow. When you have finished this lesson, demonstrate your understanding of the material by taking the progress check on the following objectives. First, describe the function of the electronic module in the governor. Second, identify the differences between the ISOC and droop conditions. Here is your instructor.
During engine operation, the governor will maintain a controlled engine speed. The governor will also maintain equal load sharing between two or more generators operating in parallel, and it will ramp the engine speed between 90 and 100%. Now let's take a closer look at the governor, which is located here inside the control console. The governor consists of 4 individual solid-state electronic modules mounted on one board. The load sensor, which is located here, functions in either the ISOC or droop mode of operation and senses generator load output. Next to the load sensor is the speed sensor, which monitors engine speed and sends a speed signal to the amplifier. The amplifier is located here and receives signals from the other 3 modules. Next to the amplifier is the ramp generator. The ramp generator controls engine acceleration between 90 and 100% speed and provides for reduced engine speed during compressor cleaning. The governor receives signals from a magnetic pickup and from current and potential transformers. The governor sends signals to the servo actuator to make adjustments in engine speed. Let's take a closer look at how engine speed is in fact controlled. Remember, engine speed controls the output frequency of the generator. To control engine speed, the governor must have 2 signals. 1, indication of actual engine speed, and 2, an indication of what engine speed should be. The governor receives an input from magnetic pickup G351 located on the reduction drive gearbox. The magnetic pickup monitors the rotation of a gear and sends a signal to the governor indicating the speed of the engine. The speed sensor then sends the speed signal to the summing junction. The signal indicating what the engine speed should be comes from the speed adjust switch. The reference signal is controlled by adjusting speed adjust switch S151. Now this reference signal of what engine speed should be is sent to the summing junction with the actual speed signal. At the summing junction, the two signals are compared. If there is a difference, an error signal is sent to the amplifier. The amplifier will then send a signal to the servo actuator to increase or decrease the fuel flow to the engine. Now let's see what happens when engine speed falls below the speed indicated by the reference signal. The speed adjust switch has been set for 60 hertz. The speed adjust switch will be sending a constant reference signal of 60 hertz to the summing junction, indicating that you want an engine speed of 60 hertz. On the other side of the summing junction, the magnetic pickup is sending a signal to the speed sensor, indicating an actual engine speed of 59 hertz. The speed sensor sends this actual signal to the summing junction. At the summing junction, the reference signal of 60 hertz is then compared to the actual signal of 59 hertz. The comparison yields an error signal which is sent to the amplifier. The amplifier then sends a signal to the actuator, causing it to retract and increase the fuel flow to the engine as required. When the magnetic pickup sends a signal indicating that 60 hertz engine speed has been reached, the error signal will cease and the throttle will hold the engine steady at 60 hertz. Now remember, the speed control section of the governor compares a reference signal sent by you with the actual speed of the engine and adjusts the engine speed to match the reference signal. The ramp generator module prevents the engine from going in overspeed as it accelerates from 90% speed. To prevent an overspeed shutdown, the ramp generator slowly increases the fuel supply to bring the engine to 100% speed. The second major function of the governor is load sharing between generators operating in parallel. The load sensor part of the governor automatically balances the kilowatt load between the two generators. Load sharing is accomplished by comparing kilowatt load signals between the parallel units. Each of the parallel units sends a signal to the governor where the two signals are compared against one another. When the load becomes unbalanced, the load sensor circuits of each governor send signals to the summing junction. If generator set A is carrying more load than B, a signal is sent to set A's actuator, causing it to decrease the amount of fuel going to the engine. Set B's actuator will move, causing it to increase the fuel flow to the engine. The fuel will continue to change until there's an equal load share between the two generators. Remember, the change in fuel flow only changes the amount of load each generator can carry. It does not change the speed of the engine. If engine speed were to change, the generator's output frequency would change from the needed 50 or 60 hertz. Now, you can select two modes of speed control for the governor by selecting either the ISOC or the droop mode with this switch. ISOC is used when you are paralleling two identical governor systems. The speed of the two will remain constant as the load is increased or decreased. Droop is used when paralleling a generator with an infinite bus or with dissimilar governors and engines. When load increases, the speed of the engine will decrease to preset levels.
When in the ISOC mode, the engine speed is maintained at a constant level as set by the speed reference level. You can see on this graph that when in the droop mode, engine speed will decrease as load is added. The engine speed will normally droop about 4% or to the amount adjusted on the governor as load is increased to full load, and the speed will increase as load is decreased.
Load sharing is automatic in both ISOC and droop mode.
You have just viewed the lesson on the governor system. Let's review important points. The load sensor monitors generator load and has a switch to select speed, ISOC, or droop. The speed sensor receives a signal from a magnetic pickup and monitors engine speed. The ramp generator module provides for reduced speed control during compressor cleaning and controls engine acceleration between 90 and 100% speed. The amplifier amplifies signals from the load sensor, speed sensor, and ramp generator and sends the signals to the servo actuator. The ISOC position of the speed, ISOC, droop switch will maintain a constant speed output at all load conditions and will maintain an equal kilowatt load between both units. The droop position allows the engine speed to drop slightly with increases in generator load. Speed increases slightly as the load is decreased. You have just completed this lesson. Now turn to your learning guide for review. If you wish to test your understanding, stop the tape and take the progress check. Lesson 5, Start Logic. The logic chart and start sequence will provide you with a roadmap when troubleshooting your engine. You will be able to trace the start sequence and determine the source of the problem. When you have finished this lesson, demonstrate your understanding of the material by taking the progress check on the following objectives. First, demonstrate the ability to correctly read a logic sequence. Second, demonstrate the ability to correctly read a start sequence chart. Here is your instructor.
You have seen in the 4 previous lessons of this module that the electrical system controls the major functions of the engine. It is in fact the components in the electrical system that time, monitor, and activate other components into operation at the appropriate time in the sequence. For example, it is the electrical system that monitors oil pressure during the engine start sequence. And it is also the electrical system that activates a pilot control valve which allows the variable vanes to open and close. Now, each of the systems on the package is monitored or controlled by the electrical system. Since the electrical system is the one common thread through all the system, and since it is the controller, we can use it to map all of the events. Each event that occurs on the package is described in a logic chart. Now, there are several types of logic charts. The block and written logic are the most common. The block logic is a type of graphic map with each of the events enclosed in a box. In this lesson, we will be using the written logic where each event is written out. At the top of each written logic, there is a legend that describes the symbols used in the logic chart. For example, an X at the beginning of a line indicates that a component has been energized. Similarly, a line with a DE at the beginning indicates that a component has been de-energized. The numbers down the left-hand side of the chart indicate the component's location on the schematic. For example, we see that KT220 is at zone 17. If we check the schematic, we will find KT220's location. The logic chart is read down the page line by line. The various events that occur can be described as either a main event or a subsequent event. The two are distinguished according to their indentation. The closing of CB501 is a main event and is placed in the far left-hand column. After CB501 is closed, there are 4 subsequent events that occur as a result of CB501 being closed. The four events are indented to indicate what happens after CB501 is closed. CB502 is another main event and is placed in the far left-hand column. CB207 is a subsequent event occurring after the closing of CB502 and is indented to the right. To read the sequence of events during startup, you read down the page. First, start with the main event, then continue by reading all of the subsequent events that occur as a result of the main event. Now let's take a closer look at the prelude sequence on the written logic chart. The main event is pressing the start switch, which is followed by two subsequent events. The start delay timer, KT20-1, is energized and it begins to time as indicated by the T. The second event to occur after depressing the start switch is the energizing of the start run relays, K210. The next main event is the timing out of KT220-1, which causes the transfer of contacts in KT220-1. KT220 is then energized, causing KT220 contacts to transfer. These contacts cause K221 to energize. K221's contacts transfer, energizing K221-1, which causes the transfer of contacts in K221-1. And finally, the DC pre-post loop pump is energized. As you can see, the logic chart is read from top to bottom to determine the sequence of events occurring during engine startup. Now we can also use the logic chart to determine all of the events that are controlled by a set of contacts, a switch, a relay, and so on. Let's see what happens when the contacts of KT222 transfer. If we lay a ruler beside this column, we will be able to see all the events that are caused by the prelude timer timing out. Contacts 5 to 1 and 6 to 4 are transferred. If we move the ruler one more column to the right, we will see what occurs after contacts 5 to 1 transfer. In this case, there are three events. The starter relay is energized, and the two primary fuel valve solenoids are energized. With this information, we can begin to troubleshoot malfunction in the start sequence. For example, if the start valve solenoid failed to energize, we can trace back through the logic to determine what caused the malfunction. At each step, we will need to check to see if the switch, relay, or contacts were energized or transferred. Once the malfunction is isolated, the parts or components can be repaired or replaced. Now, another useful tool for troubleshooting is the start sequence. Start sequence illustrates the relationship between time, speed, mechanical events, and electrical events. Across the top of the chart is the engine speed, and down here is elapsed time. The top half of the chart indicates when the electrical events occur in relation to time and speed. The bottom half of the chart indicates the mechanical events in relation to time, speed, and the electrical events. Now, we can use the start sequence chart to isolate a fault if we know the time and speed at which the fault occurred. If the engine shuts down at 15% speed plus 5 seconds, we can isolate the probable causes. We begin by determining what conditions need to be met at 15% speed for the engine to continue the start sequence. By looking at the mechanical events, we find that prelude pressure must be 41 kPa. The starter must be on, and both fuel valves must be closed. Our first step is to verify that each of these conditions was met. For example, if prelude pressure did not reach 41 kPa, we can isolate the malfunction to the oil system. Or if the secondary fuel valve did not close, we can isolate the malfunction to the fuel system and the components that control it. Now remember, we are only concerned with the events and conditions of 15% speed the malfunction occurred. By checking those events and conditions, we can isolate the malfunction to a particular system and disregard those events that are unrelated to the system.
You have just viewed the lesson on the start logic. Let's review the important points. The logic chart will help you understand the start sequence and will serve as a roadmap for the schematic. Always check the legend before you start to read a new logic, as the symbols may vary from one to another. The start sequence chart describes the events in sequence and their relationship to the events occurring in other systems. The start sequence chart can help you trace the events of a start failure and to isolate the problem. You have just completed this lesson. Now turn to your learning guide for review. If you wish to test your understanding, stop the tape and take the progress check.